Power, prevent power interruptions, outages, establishing energy efficient dual climate zones. Dual zone cooling is something we'll get into a little bit later on in the slides, but it's something a lot of people still can't wrap their head around. It's actually a use of having two zones within one enclosure for cooling and its benefits. Battery cabinets and compartments, and basic rectifiers, telecom shelters, base stations are all possible applications for DC air conditioner. Let's give you some water. So this is an example of an off-grid site. You have either solar, wind, and this is a small example. I have a better example later on in this slideshow. But you have your battery bank and you have your device. So in dual zone cooling, what we like to think is you have the primary cooling, which covers everything, whether you use a big backpack air conditioner or free cooling or whatever else. And then you have what you really want to concentrate on, maybe your batteries. So you might have a battery bank where you use a DC air conditioner just to focus on that small area. So thus the two zones, one and then two. We'll get into more a little bit later. Not sure if this is just a basic animation on an air conditioner, process the heat transfer. And obviously it's pretty basic. Everyone here I think is aware of the basic heat transfer process. And that's a little grainy. Okay, so for engineers, I don't know if that's here, thermodynamic is simple right here. Air conditioning is the process of transferring heat from inside the shell to the outside. To do this, energy is consumed in the form of quote-unquote work through the variable speed compressor and fans. As you can see over here, it's your basic, and then you have your thermodynamic flow equation. So as I said, the basic, but so as the previous slide said, and we jumped into this, obviously AC voltages are fairly popular right now, or always have been. So DC's gaining momentum right now. I would say in the past few years. Matt, if you want to speak to that, Ken. We do have someone that we just brought on within our company who's from the DC field and has had quite a bit of success in it, and we're seeing gain quite a bit of momentum over the last few years. But just to kind of point out that obviously DC is going to be more efficient than AC voltage. So right here you have total usage watts during kind of the worst time being plus 55, minus 55 C. And this is the total amount of wattage, so you have DC versus AC. So, and that's the difference and kind of the runtime efficiency. And it's able to do this through, gain the efficiency through true DC motors and variable speed fans and compressors. What is variable speed technology and how does it work? Variable speed systems work by connecting the motor control drive to the compressor and then connecting the lineup of power from the utility to the drive. The drive uses frequency modulation to adjust the power output of the compressor, enabling it to speed up or down according to the cooling load that is needed in the enclosure. So again, precise cooling based on variable speed to gain that set point. This ability to modulate compressor capacity enables many of the advantages of variable speed technology, including improved efficiency and reliability. So variable speed technology enables this kind of efficiency for three main reasons, and these are pretty important reasons, especially when we're using a case study. Again, there's that more precise load matching, less cycling on and off, especially if you have that variable speed versus an AC voltage. You're going to have that hard surge, hard current every time it pops on, short cycles, low amp, gradual pressure motor startup. Over here, this is another one for us anyway. We have our control board, compressor, the fans aren't pictured, but the control board speaks. They all speak together and talk. It tells us how much cooling is needed, how fast to run. Okay. Another advantage of the DC, improved reliability. With the addition of power electronic controls, variable speed technology is able to protect itself from failure in ways a traditional AC voltage air conditioner are capable of. This is due to the motor control drive receiving power input from the utility line before sending power to the compressor. The drive acts as a shield to protect that compressor from harmful circumstances. Additionally, the drive is constantly monitoring, adjusting the power required from the compressor motor to ensure optimal compressor and system operation. Example, the drive senses an unusual torque load on the motor because of the adverse outdoor conditions, which obviously could lead to failure if not corrected. It will reduce the power of the compressor and proactively prevent it from damaging it. Improve reliability. The advantages, it's compact and easy to integrate. You can see the little battery bank right here. This is the small DC size that we offer. Designed only for small battery compartments and cabinets and shelters. Again, there's dual zone, makes dual zone cooling efficient. Adjustable set point. Again, there's the precise cooling with variable speed to maintain the set point. And more efficient than TEC. Obviously with the TEC, it's kind of, I see it as a wash. It kind of uses more energy than it should to be claimed efficient. With the dual zone, dual zone, you want to look at it like in your house, you would keep your refrigerator open to cool your whole house. That's why you have two kind of zones. You have your primary, whether it's a heat pump or an air conditioner, and then you have obviously something for the refrigerator to keep that cool. That's kind of the basic premise to kind of put it in layman's terms. So the main focus of DC advantage, unlike conventional AC, single speed motors, the variable speed motor runs at a wide range of speeds to precisely control heated and cooled air throughout the enclosure. And the better airflow has two major benefits: electrical efficiency and cooling efficiency. Electrical efficiency, the variable speed motors will actually save you money on your energy bills as they consume less electricity than your standard AC motors. Cooling efficiency, but that variable speed technology also leads you to gaining air conditioning efficiency and your SEER, your seasonal rating, environmental energy rating. So this is the case study that we did overseas just recently. As you can see, we have 3 enclosures. This is the test conditions. 2 weeks, each enclosure had an 800 watt heat load. Each enclosure had a 1000 watt air conditioner, and the set point was 25. However, these 3 units are a little bit different. You can see the AC voltage right down here. It's just on off. We have a DC that's just on off, and we have the variable speed, which we're talking about with that precise cooling. That's the results. You can see the total kilowatt hours, 131 for the AC voltage air conditioner, was just on off. The DC on off went down drastically, and the DC air conditioner, which is capacity control with that precise cooling, is down a little bit more. That's actually what, almost about 60%, 55% from the AC on off. So we put each in graphs. So you can see set point here. So you're getting what, 7 or 8. So look at this, look how big this gap is, not to mention the surge up, down, down, down. So that's not a very tight management temperature control wise. So 7 to 8 to 25, as you can see going constantly. DC, this is the DC on off, not the capacity control. It's getting a little bit tighter. So it's 12 to 13 up to the set point. And that's from that tightening of the gap, you get your savings that we showed before in the previous slide. And the capacity control, much tighter. That management, thermal management, temperature is maybe 16, 17 set point. So it gains even more additional savings. And that's what you want, is the precise cooling, variable speed, instead of having that surge up and down, up and down, up and down. You have a nice cool line. This is kind of a mishmash of both. You can see capacity control, nice line, and then right here, whereas the on-off is all over. And these, this axis is the RPM for the compressor. So you can see how how much it's going up and down constantly. Will inevitably shorten your life of your compressor. So, based on this study, variable speed DC air conditioner was more efficient than both the AC voltage and the on-off DC. Compressor ran at a slower speed, which we average overall did. Obviously, from slower speed, you're going to get less of a draw current, and it has a lot more stable temperature control, which we showed and did a graph of that nice tight line. Instead of having that hard surge and the temperature differential from 7 to 8 C all the way to 25 to 26. So dual zone, this is kind of a brief picture of this little air conditioner right here. Again, like I mentioned, it's like a refrigerator in your house. So say this is your typical enclosure. You have your primary cooling, whether it be a backpack or free cooling or however you want to use it. And you have this little guy right here, with batteries or whatever you want to do, and then you put this guy on it. So what the whole premise behind this is to expand your delta. So if you need to keep this guy at 20 or 22 or 25 or whatever, and this whole area can be kept at 35, and then you're expanding your delta, and you don't have to turn your backpack on or your air conditioner or whatever just to cool everything in here just as a result of this guy. You can minimize him and isolate him for cooling purposes. Now I've had people say, okay, so we're going to have two solutions instead of one. Okay, your CapEx, if you're using a DC, your CapEx is going to be a little bit higher, but in the long run, it's going to save you in your ROI efficiency and energy savings. This is it's pretty much almost the same example. You have the little battery guy right here, and then you have free cooling this time. So if you want to use your dual zone cooling, instead of a big backpack 230 volt, you can use something small like a 48 volt to even have more energy savings as well. Oops. So that, like I said, the whole premise is to be able to expand that delta and be able to isolate maybe a very small area for you to focus on constantly instead of turning your primary cooling on all the time, just to keep that one little area. This is not the best of examples of dual zone, but it proves a point. So you can see we have free cooling right here. What we did is we used this with about a 1.5-ton air conditioner. It's called a parasol site. This whole up here. What we did, this was about 3 years ago. After about 2 years of running it, they had a PUE of about 1.13, which is, optimal would be 1, but that's very good. And that's kind of the basic excuse me, premise of the dual zone. You just don't want to use this guy constantly. You want to use something else along with it that will lower your energy efficiency. You don't have to keep having a hard surge every time you turn this on just to cool the inside a few degrees. So it's about working in conjunction with each other to save money and ROI, improve that ROI in the long run. DC applications, we have these all over the world. Some in Nigeria, this battery backup cabinets. Bangladesh, we have some as well. And Africa, specifically South Africa, they are implementing a dual zone cooling where they're actually using both sizes, a couple different sizes of the DC air conditioners, one for the battery and then one for the actual, their quote-unquote primary cooling. These are, almost all of these are off-grid, especially this South Africa one. So to recap, DC, precise cooling, variable speed to achieve your set point. You have feature lower energy consumption, reduction of energy costs, faster ROI, lower power infrastructure, variable speed compressor. You have that tighter temperature control like we saw on that last slide, that case study. Lower energy consumption. Variable speed fans are also going to give you lower energy consumption as well as lower noise. DC power can act as emergency cooling. you have loss of grid power, soft start, which is one of the big selling points of DC versus AC. You don't have that quick inrush, hard inrush like you would with an AC. And low voltage shut off, which shuts off intentionally when the supply gets too low, predetermines that point, which we can do based on a controller. So I know recently we had talked about CapEx, DC versus AC. I know a few years ago, your DC air conditioners were 3-4 times as much as the AC air conditioners. Actually, nowadays they're maybe only actually 2 or 2.5 times. So versus a few years ago, it is kind of trending in that right direction. Because I know a lot of people, in talking to prospective customers and things like that, they're very concerned about the CapEx because as much as you get with DC, obviously they think it comes with a cost, but it's not as much as it was used to be as far as that. So it is kind of evolving into a better solution overall. Thank you. Questions?
You know that the system is first the gas. You don't know what
Which one are
the
you looking
first
at?
one, the one you compare the 60 watt. The first comparison we have the 140 versus 74 and 60.
The case study?
Yes.
Yeah, there was 1,000 watt. They're all 1,000 watt air conditioners. Anyone else? You want to add something, Matthew? No?
Everybody's well versed with 1,000 watts. It's basically 3,300 BTU. That helps.
2.5.
What's that?
Around 2.5. 2.5.
No.
No.
3,300.
Or 3,000.
It's just under 4,000.
It's just under our 4,000.
Yes.
Yeah. No, that's a smaller.
Anybody else have questions? Comments? Thank you for coming. Appreciate it. That's it. I know it's kind of short and sweet. So.